Okay, let's take a look at a couple of economics applications having to do with maximizing revenue, and I'll say what all that is here in a second. So the demand curve is the number, and we will denote that by N of P. It's the number of things that we sell as a function of the price P. And I'll say a little more about this object in a minute. The revenue is the amount of money that we take in, and we'll write our revenue as a function of price. If someone says they have $1 million business, that means that's the amount of revenue that they take in per some time period. Economists would know more about that than I would. And then certainly the profit to the business, it's the revenue, so the amount of money that you take in minus the cost that it costs to make a particular good, right? So this is not the cost to the customer, it's the cost to the manufacturer. So let me say a little bit more about the demand curve. Okay, about this demand curve now. So the number of goods that you sell, right, that means that consumers demanded that many things that you are selling. So in this course, I'm going to write the number of goods sold as a function of the price. I think in economics courses, they switch these two things. They write the independent variable on the vertical axis, and they write the dependent variable on the horizontal axis. That's the opposite of what we do in a math course. So I'm going to go with the notation that we usually go with in a math course. So price versus the number of goods sold, we should expect that the higher the price is, the fewer things that you will sell. We will always assume in this course that the demand curve is linear. So it will always have this form. Remember the old mx plus b. So here, as you can see, the slope is negative. So if m is a positive number, then we will write N of P is equal to negative m. So this is a negative number, negative slope, negative MP plus b. So most of the problems that we will look at will have to do with maximizing revenue. And in order to write revenue as a function of price, we know that that's, right, revenue is the number of goods that you sell times the price. So one thing to keep in mind here, that if we know what the number of goods sold is as a function of price, then the revenue that we will bring in as a function of price, it's just P times N of P. And if you want, you can substitute N of P with this linear function. So we would get P times negative MP plus B. And so if we want to maximize revenue, then we really need to maximize this thing. So we want to find how much, right, what price should we charge in order to get a maximum revenue. All right, here's an example from agricultural economics. So an 8 billion, so 8 times 10 to the 9th, an 8 billion bushel corn crop brings a price of $2.40 per bushel. A commodities broker uses the following rule of thumb. If the crop size is reduced by X%, then the price is increased by 10X cents. What price will result in the maximum revenue, and what is the crop size that will result in the maximum revenue? Once we find the price, then we will have found the crop size. So let's deal with that first. And before we get into the revenue, the first thing I want to do is to write down the demand curve in this case. Okay, so now we just want to find the demand function in this situation, and this is pretty much the hard part. Once we do this, then the optimization part is pretty easy. So let's just look at the data that we have. We know that when we have 8 billion bushels, then we get to charge $2.40. In other words, right, in the P comma N, or P, the price comma the amount, when we charge $2.40, we sell 8 billion bushels of corn. So that means at this point, 2.40 comma 8 billion is on this line N of P, right? It's on the demand curve. So we'll make use of this in a second. When we reduce the crop by 1%, then we get to charge 10 cents more. So if I reduce the crop by X percent, then I get to charge 10X more cents, right? So let's just see what happens when X is equal to 1, right? So 1% of 8 times 10 to the 9th, or 8 billion, is 8 times 10 to the 7th. So I know that when the crop is reduced by this much, so if I reduce the original crop by 1%, then I get to charge $2.50. In other words, when the price is $2.50, I get to sell this much of the crop. So 7.92 times 10 to the 9 bushels of whatever crop. In this case, it's corn. So now, assuming that the demand curve is linear, we've got 2 points on the graph of this thing, so that's all we need to completely describe it. Right, so we've got this 2.40 comma 8 billion, and we've got this other point 2.50 comma 7.92 billion. So remember how to find the slope, right? All we need to find the linear function is a slope and a point. So it's the difference of the y's, so 8 billion minus 7.92 billion, over the difference of the x's, and make sure you keep them in order. So over 240 minus 250. And so if you like, you can work all this out on a calculator or do it by hand. Notice here in the denominator we got negative 10 cents. That's going to make this fraction negative. Remember, we want the slope to be negative, and so it is. And so in this case, we get negative 8 times 10 to the 8th. And so once we have a slope and we have 2 points, we can write down the equation of the line using this old point slope. So y minus one of these y coordinates, it doesn't matter which one, is equal to the slope m times x minus one of these x coordinates. So I'm going to use this one. So I've got my y, which is N of P, minus the y coordinate, is equal to the slope, negative 8 times 10 to the 8th, times P minus the x coordinate, so P minus 240. So here's an expression of the demand curve. Now I'm just going to add 8 times 10 to the 9th, or I'm going to add 8 billion to both sides, just so I can solve for N of P, because we'll want an expression just solved for N of P. So now in the next slide, we can write down a function for the revenue, take a derivative, set it equal to 0, and solve for P. Okay, now finally we can go ahead and finish the problem. So remember our demand function, the number of items, the number of bushels that we will sell as a function of the price P that we charge. That's 8 billion minus 8 times 10 to the 8th times P minus $2.40, or P minus 2.40. So this is the function, the linear function that we found on the last slide. So now remember, if this is the number of bushels that we get for a price P, then the revenue we will get for a price P, it's the price times the number of bushels. So P times N of P. So I just take P and multiply it by this expression up above here. And so when I simplify all of this, and be careful, right, negative times a negative is a positive when you work this out. Make sure you don't forget to distribute the negative sign properly. So when I work all this out, I get 8 times 10 to the 8th times the quantity 12.40 P minus P squared. So to differentiate this thing is easy. It's just a polynomial. So the derivative of the revenue now is the constant, which is 8 times 10 to the 8th, and then times the derivative of the thing in the parentheses. So the derivative of 12.4 P is just 12.4 minus P squared, so now that becomes minus 2P. And so we set this thing equal to 0, so when is this function equal to 0? Well, it must be the case that the thing in the parentheses is equal to 0. So you can easily see by inspection or by a little bit of algebra then that P must be $6.20. So this is the price that we should charge in order to bring in the maximum amount of revenue. What's the amount of the crop that we should sell to bring in the maximum amount of revenue? Well, this is the price. This is the amount of crop as a function of price. So you just take $6.20 and plug it into this thing, right? So this is the number of bushels that we should sell in order to maximize revenue. Let me not work all this out. I'll leave it to you to just take 620, plug it in for P, and then run this through a calculator. Okay.